Okay, let us move on. In the last class, we started with coordination numbers and structures of complexes, and we have defined what a coordination number is and what influences the coordination number. So here's a brief review of that. The coordination number is the number of points of attachment between the ligands and the metal. And the main factors that are determining the coordination number are the shape and the size of the ligands, the size of the metal ion, the electron configuration of the metal ion. And when we are in solid state, then there can even be intermolecular interactions that influence the coordination number. So overall, you see that there are many factors, and therefore it's difficult to predict the coordination numbers and finally on the shapes of the complexes, but there are a number of rules that can make predictions with fair accuracy. So for that reason, let us go now through all the coordination numbers step by step and see under which circumstances we find certain coordination numbers realized and what shapes are associated with the different coordination numbers. So let us start with the smallest possible coordination number. That is the coordination number 1. So when would you expect it? So first of all, in many cases when you seem to have a coordination number of 1, the coordination number of 1 is actually not realized. Generally, the coordination number 1 is very rare because it leaves many sides of the metal exposed. That's not favorable energetically, and so typically such a species tends to add more ligands, thereby increasing the coordination number. So for instance, when you look at methyl lithium, a common reagent in organic chemistry, then that seems to have a coordination number of 1, or the lithium seems to have a coordination number of 1 because it seems that there's only 1 carbon bound to the lithium. However, that's not the real structure of methyl lithium. Methyl lithium is actually a tetramer in which you have a tetrameric lithium cluster, and that cluster can be derived from a cube. So you have in this methyl lithium actually 4 lithium atoms that are arranged in a near tetrahedral fashion, okay, building a tetrahedral cluster, as you can see here. And then the remaining corners of the cube in which this tetrahedron here is inscribed are occupied by the methyl groups, and the methyl groups are actually located above the face centers of this tetrahedron here. Okay, so you see this here, 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 and here. So overall, that gives a near cubic molecule shown here in the middle. And in this view, you see that the 4 methyl groups and the 4 lithium atoms make a shape which is approximately a cube. Okay, so certainly we do not have here the coordination number of 1. The coordination number is unstable, and to stabilize the monomeric compound with the coordination number of 1, you get this cluster, which you then have in increased coordination number. So according to this view, this lithium atom would be bound to 1, 2, 3 carbon atoms, and each carbon atom would, well, interact with 3 lithium atoms, vice versa. So under which circumstances could you then realize really a coordination number of 1? This is only possible when you use extremely bulky ligands that fit around a metal extremely well, thereby preventing the metal from coordinating to other ligands. So one very rare example is this thallium compound. We see that there is one thallium which is bound to a carbon atom that is part of this very bulky linker here, which has 3 interlinked phenyl groups that have here these 1, 2, 3, 4 bulky isopropyl substituents. So this linker here wraps around that thallium very effectively, thereby preventing that thallium to coordinate to other ligands, including solvent molecules that can also not coordinate. So how do you make this compound? We can make it from the respective lithium compound. So the lithium compound is actually not in the coordination number 1. There are actually solvent molecules attached to it, 2 ether molecules. And then when you take a etheric solution of this molecule and react it with thallium chloride, then you get a metathesis reaction. The thallium coordinates to the carbon, and you're forming lithium chloride. And that happens at 0 degrees Celsius. Okay, the coordination number 1 is very rare because it requires bulky ligands. So what about the coordination number 2? So for the coordination number 2, we also have generally rarity, so there are not many examples for the coordination number 2 for the same reason as for the coordination number 1. However, there are exceptions which exist for metal ions that have the D10 electron configuration. So these metal ions, they like the coordination number 2. So what are examples for these D10 transition metal ions? That's, for example, silver plus. Why is silver plus a D10 ion? Well, when you look in the periodic table, you see that silver is in group 11. So that means it has 11 valence electrons. So these are, well, 10 d electrons and 1 s electron. And when you remove that s electron, then, well, 10 d electrons are left. Therefore, silver plus is a D10 ion. The same for copper plus. So copper plus is also in 11th group. It's located above the silver. The same is true for a gold plus, which is located below the silver. Also, mercury 2 plus is an example. So mercury is in the group 12. Therefore, we have to remove 2 electrons from the 12 electrons to get an ion with 10 d electrons. So here are a few examples of linear complexes these metal ions make. So for instance, the diamine silver plus ion that we previously encountered when we discussed nomenclature is an example for that. And dicyano silver minus ion is another example. The dichloro copper minus ion is an example like this. The mercury dicyanide is an example. Dicyano orate minus is another one, as well as mercury oxide and silver oxide. So when we have a coordination number of 2, what is the structure associated with that coordination number? And in practically all cases, we have linear structures. Okay, so this one here is, for instance, the structure of the diamine silver plus, and you have a silver linearly coordinated by 2 amine ligands. Such linear coordination you have also realized for polymeric structures. So for instance, in mercury oxide, you have actually a zigzag structure of mercury and oxygen atoms, whereby you see that the mercury is linearly coordinated by oxygen. So why do we get this zigzag chain and not a completely linear chain? That's because of the electron lone pair C of the oxygen. So what is the explanation for this linear geometry? So an oversimplified picture is that when we have a D10 ion, then our D subshell is actually completely full. And so in a way, we can say, well, the d electrons in this case are not really valence electrons that in the bonding. So we have actually only the s subshell available for bonding, and that s subshell is completely empty, and we overlap our ligands with the empty s subshell of the metal, and then just because of electron repulsion arguments, we would expect a linear shape. So if we consider also the p orbitals as valence electrons, then we could also say, well, you're getting an sp hybridization, and then the ligands overlap with the sp hybridized orbitals, and this again gives a linear shape. As I said before, this is an oversimplified explanation because the 3D orbitals are actually not really inactive, and they can be involved in the bonding too, and we get a more detailed explanation of why these complexes are stable would require a more in-depth consideration based on molecular orbital theory, and we will discuss molecular orbital theory of coordination compounds later in this course. Okay, so now what about the coordination number of 3? Well, first of all, I wanted to add that when we have ions other D10 ions, then that linear shape with the coordination number 2 is only possible when the ligands are very bulky, because otherwise, again, that coordination compound has the property to add ligands in order to stabilize itself, similar to the coordination number 1. All right, so now what about the coordination number 3? So also the coordination number 3 is still considered to be a low coordination number. It's also relatively rare, except for the 10 ions that like that electron, like that coordination number. So when we have the coordination number 3, then most often we find trigonoplanar complexes. So an example is the copper, the tricyano copper 2- complex anion that you see here. And we can again explain the shape in an oversimplified way using these EPR arguments, saying that the d electrons are not really valence electrons, only s and possibly p. We account for the p electrons as well as electrons also. then in this case we can sp2 hybridize and then overlap the ligands with the sp2 hybridized orbitals to form the trigonal planar structure. Okay, now what about coordination number 4? So the coordination number 4 is not considered a low coordination number anymore. It's considered to be intermediate coordination number. So intermediate coordination numbers are the coordination numbers 4, 5, and 6, and these are the most common coordination numbers that we know. Why are they the most common ones? Well, they're the most common ones because they suit many atom sizes and also many ligand sizes. Oftentimes, well, exactly 4 or 5 or 6 ligands fit around the respective metal ions. When it's less than that, well, then we have a low coordination number, and there's lots of space to add more ligands. When we go to very high coordination numbers, it's getting very bulky, we tend to lose ligands. So the coordination number 4 is actually the second most coordination number after the coordination number 6. And the tetrahedral shape is by far the most common shape associated with the coordination number 4. Why is that so? That's because when we have a tetrahedral shape, then the ligands can adopt the greatest distance from each other, and that's energetically most favorable. So what generally favors a tetrahedral structure over an octahedral structure? So generally, when we have a high positive charge and a small ion radius resulting from the high positive charge at the metal, as well as bulky ligands, then we tend to have a coordination number of 4 and not a coordination number of 6. Also, generally, D0 ions and D10 ions prefer the tetrahedral over the octahedral shape. So here are a few examples that demonstrate that. So this is the chromate anion, and in the chromate anion you have chromium in the oxidation state +6. And a chromium ion in the oxidation state +6, well, it has a high positive charge, and because of that, it has a small ion radius. For that reason, we can say, well, it prefers a coordination number of 4 over a coordination number of 6. Also, chromium 6+ is a D0 ion, which is another argument why it prefers the tetrahedral shape over the octahedral shape. The second example, this is the permanganate anion. So we see here that we have manganese in the oxidation state +7, and manganese 7+ ion is a very small ion, okay, because it has so high of a positive charge, explaining why it likes the tetrahedral coordination over the octahedral coordination. And we look at the number of electrons, we see again that we have a D0 ion here. Okay. So last but not least, let's look at this copper complex here. So here we have a copper plus coordinated by 4 pyridol ligand. So the copper plus is a D10 ion. So certainly we do not have a high positive charge here. So this argument is not applicable in this case. But the copper plus is a D10 ion. which explains why we prefer here the tetrahedral over the octahedral shape. In addition to that, we have here relatively bulky ligands. We have 4 pivotal ligands that coordinate to the copper plus. So this is how we can rationalize tetrahedral structures. So the second most common shape for the coordination number 4 is the square planar shape. The square planar shape is not as favorable as the tetrahedral shape from the point of view of steric repulsion of ligands. However, certain electron configurations, in particular the D8 electron configuration for metal ions, favors square planar structures over tetrahedral structures. So why this is would again require a deeper understanding of the bonding in these structures, and we'll get to that later in this course. But for now, let's just accept that when we have a D8 electron configuration, then we will usually expect square planar structures and not tetrahedral structures, even though tetrahedral structures are also possible. So what are D8 ions? So for instance, in the group 10, we have nickel plus, palladium, nickel 2 plus, palladium 2 plus, and platinum 2 plus. So why are these D8 ions? Well, you need to look in the periodic table. Nickel, palladium, and platinum are in group 10 of the periodic table. So therefore, when we remove 2 electrons, we have 8 electrons left, and these 8 electrons are d electrons. Okay, therefore, these are the 8 ions. So what are examples of nickel, palladium, and platinum complexes that are square planar? So for instance, this molecule, which is called cisplatinum, is a square planar complex. We have here 2 amine ligands and 2 chloroligands binding to the platinum, whereby the amine and the chloroligand is standing in cis position. So this is an important anti-cancer drug. Another example is tetracyanonickelate 2-, in which 4 cyanoligands bind to a nickel 2 plus in a square planar fashion. How we can see that platinum and nickel are in the oxidation state +2 here and are really the 8 ions. We need to consider we have here 2 neutral ligands, the amine ligands, and 2 anionic chloroligands. So that's overall a neutral molecule here. So we have these 2 anionic ligands. Well, we need to have a 2+ charge on the platinum in order to get to a neutral compound. So here we have, well, 4 cyanoligans that have a 1- charge each. That gives 4 negative charges overall. You see that the complex has a 2 negative charge. So -4 + 2 gives -2, and therefore nickel must have the oxidation number +2. So then you can also have group 11 D8 ions. So the group 11 metals, they have 1 electron more than the group 10 metals. Therefore, you must remove 1 electron more in order to produce a D8 ion. Okay. So therefore, the copper must be in the oxidation state +3, the silver must be in the oxidation state +3, and the gold must also be in the oxidation state +3. So copper and silver are relatively rarely found in the oxidation number +3, but gold is relatively common. So silver can only be in the oxidation state +3 if oxidized with a very strong oxidant, such as fluorine. Therefore, the tetrafluoroargentate is an example of a square planar silver complex, anion, in which silver exists in the oxidation state +3 in a coordinate in a square planar way by 4 fluorine atoms. Okay. Another example is the tetrachloro orate minus. So here the gold is in the oxidation state +3. You can see this from the fact that we have these 4 chloroligands that have one negative charge each. That gives 4 negative charges. So -4 +3 gives -1, the negative charge at the anion. So can you think about other metal ions that can have a D8 electron configuration? We looked at group 10 and group 11. Can you think about another group that could make D8 ions? You may unmute yourself. Any ideas? No ideas?
You could do group 9.
Group 9, correct. And what would then be the respective metal ions? That would be, well, cobalt 1, rhodium 1, and iridium 1. However, cobalt is not stable in the oxidation state +1, but rhodium and iridium are. Okay. So in group 9, we have 1 electron less than in group 10. Therefore, we only need to remove 1 electron in order to get 8 electrons. So here are just also 2 examples for rhodium and iridium 1 complexes. So in this case here, you have rhodium bound to 3 triphenylphosphine ligands and 1 chloroligand. So this is a neutral complex. So these 3 phosphines do not carry a charge, but the chloroligand carries a negative charge. Therefore, the rhodium must carry 1 positive charge, so that the entire molecule becomes neutral. Here's an example of an iridium complex. So this iridium complex is bound to 3 triphenylphosphines, 1 chloroligand, and 1 carbonyl ligand. So again, these 3 here are neutral, and that one is negative. So because the overall complex doesn't have a charge, the iridium must have the oxidation number +1. Okay. Now we have discussed the square planar structures, whereby I should say, and I forgot that, there are other possibilities for square planar structures when we do not have a D8 ion, but we only observe this when the ligand imposes the planar structure. So for instance, the so-called saline ligand imposes a square planar structure because it is a tetradentate ligand in which the donor atoms, okay, are arranged in a planar fashion due to the structure of the ligand. Okay, so in this case, the metal ion has no other choice but coordinate in a square planar fashion. This is imposed by the planar ligand. Okay. Similarly, in a porphyrin complex, you have a similar situation. This is also a planar ligand in which the 4 nitrogen donor atoms are arranged in a square planar geometry. So the metal ion, no matter what electron configuration it has, is forced to adopt the square planar structure. It cannot adopt the tetrahedral structure. Okay, so there's a third possibility to realize the coordination number 4. That's the seesaw structure. However, we observed the seesaw structure only for main group compounds. For example, SF4 has the seesaw structure, and adopt the seesaw structure because, well, we have 4 fluorine ligands and we have 2 electron lone pairs. Okay, so these 2 electron lone pairs, they require somewhat more space than the fluoroligands here. Okay, therefore they are in the coplanar with these two fluorines. Okay, and overall the structure is derived from the octahedral structure. Okay, so if we count the 2 electron pairs also as ligands, then we would have the sulfur number 1, 2, 3, 4, 5, 6 ligands, but of course the electron pairs are not actual ligands. So basically 2 corners from the octahedron are being removed, leading to the SF4 seesaw structure. However, this structure is only known for the main group elements, and main group molecules we typically do not view as coordination compounds, and therefore we can say that the seesaw structure is actually not known for coordination compounds, but only for main group elements. Okay, now let's leave the coordination number 4 and let's go to the coordination number 5. So in the previous coordination numbers, there was always one structure which was clearly preferred. That's not the case for the coordination number 5. There are 2 different structures which are about equally common because they have approximately equal energy. And they can also easily interconvert because there's a low activation barrier between the 2 structures. Therefore, these structures are often fluxional. So the first structure is the trigonal bipyramid, and pentachlorocuprate 3- is one example. And you see that you have, in this case, 3 chloroligands that are here in the equatorial plane, and the remaining 2 chloroligands are occupying the actual position. You see that in this structure, not all the ligands are equivalent with respect to symmetry. Okay, so those that are on the equatorial plane are symmetrically different from those in the actual position. So that's also a difference to all the structures that we've previously seen, except the seesaw structure. which all ligands were symmetrically equivalent. So the other very common structure is the square pyramid. So in this case, you have 4 ligands that build the base of a square, and then that square is capped by an additional ligand. An example is the tetracyanonickelate 3-, in which we have 5 cyano ligands around nickel 2 plus iron. So as I said before, these structures are often fluxional and they can interconvert using a mechanism which is called the barrier pseudo-rotation. So the interconversion happens very easily because there's a low activation barrier to overcome. Okay, so you see here schematically how the barrier pseudo-rotation works, illustrated for iron pentacarbonyl. So if here an iron in the center and 5 carbonyl ligands around, and you see that this molecule adopts a trigonal bipyramid. However, that structure can very easily interconvert into a square pyramidal structure, which is energetically only slightly less stable. And there's little activation barrier to overcome in order to go from this structure to that structure. Why is that? You can see this very easily from the fact that the transition from here to here only requires that the bond angle between this carbonyl, and that iron becomes smaller, okay, a little smaller. And that bond angle here between these 2 carbonyls, for instance, and that iron here becomes a little bit wider, okay? And then we have a trigonal pyramid, okay? Now this process can even continue, and this intermediate here can convert into another trigonal bipyramid, whereby now the ligands that were previously in the axial positions are in equatorial positions, and 2 of the ligands that were in equatorial positions are now in the axial positions. That can happen when the angle between these 2 further narrows, okay, so that it becomes exactly 120 degrees. Then these 2 ligands here are actually now in the equatorial position, and you see that you can see that here. So these 2 here became these 2, whereas these 2 here, okay, became these 2 here, whereby now you have a 180-degree angle in between them. Okay, you see the overall process also here. So you see that this molecule permanently switches from one trigonal bipyramidal structure to another trigonal bipyramidal structure, going through this square pyramidal intermediate. And you see that the ligands move permanently from axial to equatorial positions and vice versa. Okay? So now here these 2 are axial, now they're equatorial. So now they're axial, now they're equatorial again. And for these 2 here, now they're equatorial and now they're axial. Back equatorial and axial. So because of that, when you take an NMR of that molecule, you do not actually see 2 different signals for the equatorial and the axial ligands respectively, but you actually see only 1. And that's because the equatorial and the axial positions constantly interchange. So you can, however, slow down this process by, for instance, going to lower temperatures, and then you can really resolve axial and equatorial positions. Okay, you can also slow down the Bayer pseudo-rotation by using ligands that are very bulky. That also slows down the Bayer pseudo-rotation and allows you for the observation of axial and equatorial positions. Okay. Yeah, this is just what I said before. So you have a lower activation energy, and so that pseudo-rotation is too fast for the NMR timescale. Okay, so therefore only one NMR is observed for the ligands. But when you go to lower temperatures, you slow down this process, and you can observe two different signals. All right, so now let's go to the coordination number 6. So the coordination number 6 is the most common coordination number. Why? One reason is simply that it suits the size of many metal ions and the size of many ligands. But another reason is that in the coordination number 6, when we have the octahedral geometry, which is the most common shape for the coordination number 6, many orbitals point into the direction of an octahedron. Okay, in particular the p orbitals and also some of the d orbitals, in particular the dx square minus y square and the dz square orbitals. And for that reason, the energy of the complex is minimized when the ligands approach on the axes of an octahedron, because then orbital overlap can get maximized. Okay, so that's one reason why the coordination number 6 is most common. That's one reason why the octahedral shape is the most common shape for the coordination number 6. Another reason is that for an octahedral complex, we have the greatest distance between the ligands. That's another reason why octahedral complexes are favored over other shapes in which the coordination number 6 occurs. Okay, so here's just one example of an octahedral complex. We saw that molecule before, so that's the hexacyano array. So the mine is in which 6 cyanoligans coordinate in iron octahedrally. Okay, so we know the coordination number 6 in octahedral complexes for all transition metals in all electron configurations. All right, so then we can have distortions from the ideal octahedral shape, and we can have various types of distortions. So one type of distortion is the so-called tetragonal distortion, which occurs along two opposite vertices, and we can have a so-called elongated octahedron and a so-called compressed octahedron. So in the elongated octahedron, we elongate along two opposite corners. Okay, so that leads to an elongated octahedron. Okay, when we have a compressed octahedron, rather than we do the opposite, we compress the octahedron along two opposite corners. So when you have a tetragonal distortion, then all faces are still equal with regard to symmetry, but the metal ligand distances are not equal. So in the elongated octahedron, we have 4 ligands closer to the metal and 2 further apart. And in the compressed octahedron, you have 2 ligands closer to the metal and 4 ligands further apart from the metal. So in addition to the tetragonal distortion, you have the so-called trigonal distortion. I forgot to say that we reduce the symmetry when we distort, so we don't have the symmetry OH anymore, but we have instead the symmetry D4H. Okay, so now we can also trigonally distort. So what do we do then? Then we distort, and we can again either compress or elongate along 2 opposite faces. Okay, you see here a regular tetrahedron with 2 opposite faces in red, and when we distort along these faces, then we form a structure which is called a trigonal anti-prism. Why is it called a trigonal anti-prism? This is because the resulting structure has trigonal symmetry. So we have these 3 axes here as the principal axis. And we have an anti-prism because these 2 opposite faces here are oriented in a staggered fashion, whereas in a regular prism, 2 opposite faces would be arranged in a eclipsed fashion. So in this case, are all faces being equal? The answer is no. So these 2 faces here have a different shape than the other 4. Are all metal ligand distances equal? The answer is yes. So all corners have the same distance from the center of the trigonal antiprism. What symmetry do we have overall? We have the symmetry D3D. This is because in addition to the principal axis that goes here to the center of these 2 opposite faces, we have 3 C2 axes that actually go to the center of 2 opposite edges. For instance, this one, and this one, and this one, and this one. And finally, we have 3 vertical mirror planes that bisect these 3 C2 axes, and that makes them dihedral mirror planes. Okay, then finally, it is also possible to get trigonal prisms. In trigonal prisms, the 2 opposite triangular faces are oriented in a eclipsed fashion. So that's energetically not so favorable because the ligands come closer, the distance isn't maximized, but they can occur especially when we have bidentate ligands that have donor atoms that have a distance from each other that force the structure into the trigonal prisms. So what is the point group in this case? In this case, the point group is D3H. Okay, we have a C3 principal axis, and then we have a horizontal mirror plane that stands perpendicular to that principal axis. So trigonal prisms can also be elongated or compressed, but this actually does not change the point group. All right, then let's stop at this point. We still have the high coordination numbers to cover, but let's stop at that point here, and we can stop the recording.